imagine yourself, just for a moment, sitting in a quiet, dimly lit room in the middle of a desert at night. The air is still and cool. Through a large window, you can see the colossal shape of a giant radio telescope dish, hundreds of feet across, pointed silently up at a sky overflowing with stars. Inside your control room, the only sounds are the gentle hum of electronics and the quiet hiss coming through a set of speakers. That hiss is the sound of the universe. It's a constant, gentle static, the combined whispers of countless natural cosmic phenomena. On a screen in front of you, the data streams in, a waterfall of information. You can see the steady, rhythmic pulse of a distant pulsar, a tiny spinning star flashing like a cosmic lighthouse. You can see the loud, messy crackle of a quasar, a supermassive black hole at the center of a galaxy billions of light years away, gobbling up stars. You can even detect the faint, ever-present afterglow of the Big Bang itself. For decades now, we have been listening like this. With immense, sensitive instruments, we have been cupping our ear to the cosmos, sifting through all that natural noise, listening for something different. We are listening for a signal that is not natural, a signal that is structured, that is complex, that has intent. We are listening for a beacon, a message, a greeting card, a warning, or even just the faint, accidental leakage of another civilization's daily life. We are listening for a simple, intelligent hello. And in all that time, from all those billions of stars, in all that cosmic static, we have heard nothing, only a great, profound, and beautiful silence. Tonight, we're going to explore that silence. We're going to take a long, quiet journey into one of the deepest and most fascinating mysteries there is, the Fermi Paradox.
But this isn't a story meant to make you feel anxious or lonely. It's the opposite. It's a story designed to give your mind something vast and wonderful to ponder as you drift off. We'll approach this great mystery not as a problem to be frantically solved, but as a quiet philosophical question to be gently explored. We'll look at all the possibilities, from the mundane to the truly mind-bending. The goal isn't to find an answer, but to appreciate the profound beauty of the question itself. So let's get comfortable and begin our exploration of the great silence. Before we can truly feel the weight of the silence, we first have to appreciate why the universe should be noisy. We have to build the case for why our galaxy and the cosmos at large ought to be teeming with life and with civilizations. The argument is one of pure, simple, overwhelming scale. Let's start with the stars. When you look up at the night sky, even from a dark location, you can only see a few thousand stars with the naked eye. But our home galaxy, the Milky Way, is so much grander than that. It is a vast, spinning island of stars. The exact number is hard to count, but current estimates suggest there are somewhere between 100 billion and 400 billion stars in our galaxy alone. Let's take a conservative number and just say 200 billion. That's our starting point. 200 billion suns, each one a potential anchor for a planetary system. But that's just our galaxy. And our galaxy is not unique. For a long time, we didn't know if other galaxies existed. But now, thanks to telescopes like Hubble, we know that the observable universe is filled with them. How many? Again, the numbers are staggering. Current estimates suggest there are as many as 2 trillion galaxies in the observable universe. 2 trillion galaxies, each with hundreds of billions of stars. The number of stars in the known universe is greater than the number of grains of sand on all the beaches on Earth combined. It's a number so large, it's essentially infinite from our human perspective.
So, the number of potential homes for life is not the issue. The universe is incredibly vast. The next question is, how many of these stars actually have planets orbiting them? For a long time, we had no idea. We could only see the planets in our own solar system. But starting in the 1990s, and especially with the launch of NASA's Kepler Space Telescope in 2009, we have found the answer. And the answer is almost all of them. Kepler worked by staring at a single patch of sky, monitoring the brightness of over 150,000 stars simultaneously. It was looking for tiny, periodic dips in a star's brightness, the telltale sign of a planet passing in front of it, an event called a transit. The mission was a spectacular success. It revealed that planets are not a rare exception, they are the rule. The data from Kepler and other missions suggests that, on average, there is at least 1 planet for every star in the galaxy. That means there are hundreds of billions, perhaps even trillions of planets just in our own Milky Way. This leads us to a famous framework for thinking about this probability, something called the Drake equation. It was developed by an astronomer named Frank Drake in 1961 as a way to structure a scientific discussion about the search for extraterrestrial intelligence. It's not a formula you can solve to get a definitive answer, but rather a beautiful tool for organizing our ignorance. It's a quiet, logical progression of questions. We've already answered the first parts. We know the rate of star formation, and we know that a high fraction of them have planets. The next question in the chain is, how many of those planets are in the right place for life to begin?
This brings us to the concept of the habitable zone, which you might know as the Goldilocks zone. This is the region around a star where the temperature is not too hot and not too cold for liquid water to exist on the surface of a rocky planet. Liquid water, as we've discussed in other stories, is believed to be the essential solvent for the chemistry of life as we know it. If a planet is too close to its star, its water will boil away. If it's too far, its water will be permanently frozen solid. The habitable zone is that just right orbit where a planet could potentially have liquid oceans. Based on the data from Kepler, our best estimates are that as many as 20% of Sun-like stars might have an Earth-sized planet in their habitable zone. If we do the math, that could mean there are billions, perhaps even tens of billions, of potentially habitable, Earth-like planets just in our Milky Way galaxy alone. Billions of worlds where the fundamental conditions for life could be met. And what about the ingredients for life itself? This brings us to the next part of the case for a crowded universe, the abundance of the right chemistry. Life on Earth is carbon-based. It's built from a handful of key elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. You might think that these organic building blocks are rare and special, unique to our world. But one of the most exciting discoveries of modern astronomy is that they are incredibly, almost shockingly common. We have found complex organic molecules inside meteorites that have fallen to Earth, remnants from the formation of our solar system. We see their chemical signatures in the vast cold clouds of gas and dust that float between the stars, the very clouds from which new solar systems are born. We've even detected them in the hazy orange atmosphere of Saturn's moon Titan.
The universe, it seems, comes pre-stocked with the necessary ingredients for life. The building blocks are everywhere. So, We have billions of potentially habitable planets, and these planets are likely showered with the very chemical components needed to get life started. The next term in our quiet Drake equation asks, on what fraction of these perfect planets does life actually arise? This is a huge unknown, of course. But many scientists, looking at how quickly life appeared on Earth after it cooled down, suspect that if the conditions are right, the leap from non-living chemistry to simple microbial life might not be that difficult. Perhaps it's a natural, almost inevitable outcome of planetary chemistry. If even a tiny fraction of those billions of habitable worlds develop simple life, there would still be millions of life-bearing planets in our galaxy. The final piece of the puzzle is time. Our universe is 13.8 billion years old. Our solar system and the Earth are only about 4.5 billion years old. This means the universe has had a very, very long time to work on this problem. There were billions of years before Earth even formed, when other older planets could have been circling other older stars. There could have been entire generations of civilizations that arose, evolved, developed incredible technology, and perhaps vanished completely billions of years before life on our planet even got started. When you put it all together, the sheer number of stars and planets, the abundance of the right ingredients, and the immense age of the universe, it paints a powerful picture. The galaxy should be filled with life. It should be a noisy, bustling, cosmic metropolis. The silence we observe is therefore not just a lack of evidence, it is a profound and deeply puzzling contradiction. And this brings us to the heart of our story. So, we have this immense, logical case for a crowded galaxy on one hand. On the other hand, we have what is sometimes called the Great Silence. This is the stark observational reality. Despite decades of actively looking and listening, we have found no credible evidence for any other intelligent life in the universe. The search for extraterrestrial intelligence, or SETI, has been going on since the 1960s. Dedicated astronomers have used some of the world's largest radio telescopes to scan the skies, listening for any non-natural, structured signal that might betray the presence of another technology. We have listened to millions of star systems across a wide range of frequencies, and the result has been the same every time. Nothing but the beautiful, natural static of the cosmos. We have also looked for other signs. An incredibly advanced civilization might build vast megastructures around its star to capture energy, like a Dyson sphere. We have searched for the telltale thermal signature of such structures, and we have found nothing. We have looked for the signs of industrial pollutants in the atmospheres of other planets, and we have found nothing. We have looked at our own solar system for any sign of a visiting probe or ancient artifact, and we have found nothing. The sky, for all its statistical promise, appears to be completely, eerily empty. This brings us to the famous lunchtime conversation that gave the paradox its name. The story goes that in 1950, at the Los Alamos National Laboratory, a group of brilliant physicists were having lunch. Among them was the Italian-American physicist Enrico Fermi, one of the architects of the atomic age. The conversation turned to the topic of flying saucers and the high probability of alien life. After listening to his colleagues enthusiastically discuss the possibilities, Fermi reportedly fell silent for a moment, and then asked a simple, devastatingly profound question that cut through all the speculation. But where is everybody? That simple question, where is everybody, is the heart of the Fermi Paradox. It is the stark contradiction between the high probability of extraterrestrial life and the complete lack of any observational evidence for it.
If the galaxy should be full of life, then why is it so quiet? If civilizations can arise, then at least some of them should have developed interstellar travel by now. Our galaxy is old enough that a single spacefaring civilization could have colonized the entire Milky Way in just a few million years, a mere blink of an eye in cosmic time. So why do we see no signs of a galactic empire? Why no probes, no signals, no grand projects? The silence is deafening. This is the great mystery we will explore for the rest of our time together tonight. The rest of our journey down this quiet iceberg will be a calm exploration of the many possible answers to Fermi's question. These answers range from the simple and mundane to the deeply philosophical and truly bizarre. And for our purposes, I find it helpful to group them into two main categories. The first category of solutions argues that there is no one to see. The reason the sky is silent is because we are, for all practical purposes, alone. This line of thinking suggests that there is some great barrier, some immense hurdle that prevents life from becoming common. The second category of solutions argues that they do exist, but that there is some reason why we can't see them or hear them. This line of thinking suggests that the silence is not due to absence, but to other, more complex factors. So let's begin by exploring that first, more sobering possibility. Let's drift down into the quiet, lonely solutions that suggest that we might just be the only ones asking these questions. This first set of answers to the Fermi Paradox is, in many ways, the simplest. The sky is silent because there's no one out there to make any noise, or at least no one technologically advanced. These solutions suggest that while the ingredients for life might be common, the actual emergence and survival of a spacefaring civilization is so incredibly rare that it may have only happened once here on Earth. This is the idea of the Great Filter. The Great Filter theory was proposed as a way to think about this problem. It suggests that there must be some step, some barrier in the long evolutionary path from a simple non-living molecule to a galaxy-spanning civilization that is so incredibly difficult to overcome that almost no species ever makes it past. This filter could be any one of a number of different challenges, and the most profound question for us is, have we already passed this filter, or is it still waiting for us in our future? Let's calmly consider some of the candidates for this great filter. The first possibility is that the filter is right at the very beginning of the story. Maybe the jump from non-living chemistry to the first simple self-replicating life form is the impossibly hard step. This is the problem of abiogenesis. We know that the early Earth had oceans rich with organic molecules, a primordial soup. But how did those simple molecules organize themselves into the first living cell, complete with a metabolism and a way to reproduce itself? It's one of a handful of the biggest unanswered questions in all of science. It might be a process that is so fantastically improbable, requiring such a specific and unlikely series of chemical flukes that it has only happened once in our entire galaxy. If this is true, then the Great Filter is behind us. The universe could be full of habitable planets with lifeless, chemical-rich oceans, and we are the sole, miraculous exception.
But what if simple life, microbial life, is actually common? Perhaps that first step isn't so hard after all. In that case, the Great Filter must lie somewhere else, further down the evolutionary path. The next major candidate for the filter is the leap from simple life to complex life. For the first 2 to 3 billion years of life on Earth, our planet was inhabited only by very simple, single-celled organisms, things like bacteria and archaea. These are known as prokaryotic cells. They are tiny, simple, and don't have much internal machinery. Then, about 2 billion years ago, something truly revolutionary happened. Two of these simple cells, through some kind of symbiotic merger, formed a new kind of cell, the eukaryotic cell. This new type of cell was much larger and vastly more complex. It had a nucleus to protect its DNA and tiny specialized internal organs called organelles, like mitochondria, to generate energy efficiently. This single evolutionary event was the key to all complex life on Earth. Every plant, every fungus, every insect, every animal, including you and me, is made of these complex eukaryotic cells. And as far as we know, this incredible leap from a simple cell to a complex one only happened once in 4 billion years of life on Earth. It might be the single most difficult and improbable step in the entire history of life. If this is the great filter, then the universe might be teeming with microbial slime on countless worlds, but planets with complex plants and animals could be exceptionally, incredibly rare. We might live in a galaxy of microbes, but a desert when it comes to creatures we could actually see. Let's continue down the path. Let's say that both simple life and complex life are relatively common. Where could the next great filter be? The next candidate is the emergence of what we would call intelligence. That is, the kind of intelligence that can build tools, develop language, create science, and contemplate its own existence. Evolution doesn't have a goal. It's not trying to create intelligence. It just favors traits that lead to better survival and reproduction. And for most of the history of life on Earth, high intelligence has not been a particularly common survival strategy. There have been billions of species on this planet. Dinosaurs ruled the Earth for over 150 million years, but they never built telescopes. Sharks have been perfectly adapted to their environment for even longer, but they have never pondered the stars. It's possible that the specific evolutionary pressures that led to the development of the human brain, our bipedalism freeing up our hands, our complex social structures, our development of language, are an incredibly rare convergence of events. So the universe might be full of planets with their own bizarre jungles and oceans, teeming with complex life, but almost none of them ever produce a species that looks up at the sky and asks, "Where is everybody?" Intelligence itself might be the great filter. But there is one last, much more sobering possibility. Maybe life is common, maybe complexity is common, and maybe intelligence is common. If that's the case, then the great filter might not be in our past, it might be in our future. This is the most unsettling version of the theory. It suggests that there is some technological or social hurdle that all intelligent civilizations eventually face, and that almost none of them survive.
What could this future filter be? The candidates, unfortunately, are all too easy for us to imagine. It could be the discovery of a technology so powerful that it inevitably leads to self-destruction, like nuclear weapons or engineered plagues. It could be that all advanced civilizations eventually exhaust the resources of their home planet and cause an irreversible environmental collapse before they can become truly spacefaring. It could be the creation of a runaway artificial intelligence that sees its creators as irrelevant or as a threat. In this scenario, the great silence that we observe in the sky is not an empty stage waiting for us to take our place. It is a graveyard. It is the quiet testament to the countless other civilizations that reached our level of technological sophistication and then failed to pass their final great test. This is the most cautionary version of the Fermi Paradox. It suggests that the silence is a warning, a reminder that our own future is not guaranteed. It means that we might be standing on the edge of the same great filter that has extinguished so many others before us. It's a profound thought that encourages a deep sense of responsibility for the future of our own species. This idea of the great filter is closely related to another family of solutions to the paradox, which also suggests that we are alone, or at least very rare. This is the rare Earth hypothesis. While the great filter theory focuses on a single, near impossible hurdle, the rare Earth hypothesis suggests that there isn't just one filter, but dozens, maybe even hundreds of them. It's the idea that for a planet to support not just life, but complex, intelligent life, it needs to win a long, long series of cosmic lotteries. And the chances of winning all of them are so small that Earth might be the only winner in our entire galaxy.
So let's just quietly explore this idea. Let's take a slow walk through all the things that had to go just right for us to be here, listening to this story tonight. It's a humbling checklist, a list of all the cosmic lotteries our small world seems to have won. The first and most important ticket we won was the one for our star, the Sun. It turns out that the type of star a planet orbits is incredibly important. Our Sun is what's called a G-type main sequence star, or a yellow dwarf, and it is, for the purposes of life, just about perfect. Firstly, it's stable. For billions of years, its energy output has been remarkably consistent, providing a steady and predictable source of warmth. This stability is crucial for life to have the long, uninterrupted time it needs to evolve in complex ways. Many stars are not so calm. Take, for example, the most common type of star in our galaxy, red dwarfs. These are small, cool, dim stars. While they have the advantage of living for trillions of years, they have a violent and unpredictable youth. They are known to produce incredibly powerful stellar flares, blasting their nearby planets with lethal doses of X-rays and charged particles, which would likely sterilize any world in the habitable zone. On the other end of the scale, you have the giant, hot, blue, O-type stars. These are magnificent, but they live fast and die young. They burn through their fuel in just a few million years, which is almost certainly not enough time for complex life to evolve. Our Sun is in the Goldilocks zone of stars. Not too hot, not too cold, not too violent, and with a nice, long, stable lifespan.
The next lottery ticket we won was for our location, not just in our solar system, but in the galaxy itself. Just as there is a habitable zone around a star, there is likely a galactic habitable zone. This is a specific region of the galaxy that is safer and more conducive to life than others. If you're too close to the galactic core, it's a very dangerous neighborhood. The density of stars is much higher, which means the chance of a nearby star going supernova and sterilizing your planet is also much higher. The core itself contains a supermassive black hole, and the region around it is a maelstrom of high-energy radiation. It's probably not a good place to try and nurture fragile, evolving life. But if you are too far out, in the distant, sparse suburbs of the galaxy, you have a different problem. The stars out there are often much older and more metal-poor. Remember, in astronomy, metals are any elements heavier than hydrogen and helium. These heavy elements, which are forged in stars and spread by supernovae, are the essential building blocks for rocky planets and for life itself. Out in the galactic fringe, there might not be enough of this raw material to build a world like Earth. Our solar system is situated perfectly, in a quiet, stable spiral arm, far from the dangers of the core, but in a region that has seen enough previous generations of stars to be rich in all the heavy elements needed for life. We live in a safe, quiet, and resource-rich cosmic suburb. Then there's the layout of our own solar system. It's not just about our planet, but about our neighbors. In particular, it's about our big brother, the giant planet Jupiter.
Jupiter's immense size and gravity have made it a critical player in the story of life on Earth. It acts as a kind of cosmic bodyguard, a gravitational bouncer for the inner solar system. The early solar system was a much more chaotic place than it is today, filled with countless comets and asteroids left over from its formation. Jupiter's powerful gravity has, over billions of years, cleaned up our neighborhood. It has likely ejected trillions of comets and asteroids from the solar system, flinging them out into deep space. It has also absorbed the impacts of many others itself. In 1994, for example, astronomers watched in awe as the comet Shoemaker-Levy 9, which had been broken into more than 20 pieces, slammed one by one into Jupiter, leaving massive dark scars in its atmosphere, some of them larger than the Earth. If Jupiter hadn't been there to take that hit, that comet could have been heading for us. Without Jupiter acting as our faithful bouncer, the Earth would have been subjected to a much more frequent and much more intense bombardment of large impactors. While some impacts might be necessary for delivering water and organic molecules, too many large ones would act as a constant reset button, causing mass extinctions and preventing complex life from ever gaining a permanent foothold. The quiet, distant presence of Jupiter has been essential for giving Earth the long period of relative peace it needed to flourish. And now we come to our closest neighbor, the most prominent object in our night sky, our moon. And here we find another piece of extraordinary luck. Our moon is not a normal moon. It is, relative to the size of its planet, unusually and profoundly large.
Most planets either have no moons at all, like Mercury and Venus, or they have a collection of very small moons that are likely just captured asteroids, like Mars. The gas giants have large moons, but relative to the immense size of the planets themselves, they are tiny. Our moon is over a quarter the diameter of the Earth. This makes the Earth-Moon system function almost like a binary planet system, two worlds dancing together through space. And this large, close companion has had at least 3 profound and potentially life-critical effects on our planet. The first, and perhaps most important, is stability. The Earth, like all planets, spins on an axis, and that axis has a natural tilt. This tilt is what gives us our seasons. But the gravitational pulls from the Sun and the other giant planets are constantly trying to tug on the Earth and change its tilt. Without our large moon and a close orbit, these tugs would cause Earth's axial tilt to wobble chaotically over long periods of time. Its tilt could swing from almost zero, creating no seasons, to extreme angles, creating unimaginably severe differences between summer and winter. This would lead to wild, catastrophic swings in the global climate, making it incredibly difficult for complex life to survive and adapt. Our moon's gravity acts like a powerful, stabilizing gyroscope. It holds the Earth's tilt steady, giving us the predictable, relatively calm climate that has allowed life to thrive. The second effect is the tides. The moon's gravity pulls on Earth's oceans, creating the familiar rhythm of high and low tides. This constant ebb and flow created vast tidal pools on the early Earth. These pools would be repeatedly filled with water rich in chemicals and then baked by the sun as the tide went out, concentrating the chemical soup. Many scientists believe these tidal pools were the perfect natural laboratories, the ideal chemical kitchens for the very origin of life itself.
And there's a third, more subtle effect. The early Earth spun much, much faster than it does today. A day might have been only 6 to 8 hours long. The moon was much closer to the Earth back then, and its powerful tidal forces acted as a gentle brake on the Earth's rotation. Over billions of years, this tidal friction has slowed our planet's spin down to the familiar 24-hour day we have now. This slower rotation has likely contributed to a more moderate climate and less extreme weather patterns. So our large, beautiful moon isn't just a pretty object in the night sky. It may be one of the key reasons we are here at all. Finally, after looking at our star, our galactic neighborhood, our solar system, and our moon, we come to the Earth itself. And even here, we find features that may be incredibly rare. The most important of these might be plate tectonics. Our planet's crust is not a single solid shell. It is broken up into a series of large plates that are constantly, slowly moving around, floating on the semi-molten mantle beneath. This conveyor belt of the Earth's crust is responsible for earthquakes and volcanoes, but it also acts as a critical long-term global thermostat. Volcanoes release gases, including carbon dioxide, into the atmosphere. At the same time, CO2 is pulled out of the atmosphere by reacting with rainwater to form carbonic acid, which then weathers rocks on the surface. This weathered material eventually gets washed into the oceans and subducted back into the mantle at the boundaries of the tectonic plates. This entire process, called the carbonate-silicate cycle, acts as a giant natural feedback loop regulating the amount of CO2 in our atmosphere over geological time and keeping our planet's climate from spiraling into a runaway greenhouse effect, like Venus, or a deep freeze, like Mars. It's a subtle, planetary-scale process that has kept our world habitable for billions of years.
And of course, there is our planet's strong magnetic field, generated by the churning of its liquid iron core. This invisible shield protects us from the solar wind, which would otherwise strip away our atmosphere and boil away our oceans, just as it did on Mars. So, when you add up all these factors, the right kind of star, in the right part of the galaxy, in a solar system with the right kind of planetary bodyguard, orbiting with the right kind of oversized moon, on a planet with the right kind of geological activity and a protective magnetic field, you start to see the argument. The rare Earth hypothesis suggests that this list of requirements is so long and so specific that the chances of finding another planet that has won every single one of these lotteries might be vanishingly small. We might not be the only planet with life, but we might be the only one with a rich, complex biosphere and an intelligent civilization. We might simply be the rarest thing in the universe. And so, this brings us to the end of our first major category of solutions to the Fermi Paradox. These are the lonely solutions. Whether it's because of a single great filter that almost no life can pass, or because of a long series of smaller hurdles that make a planet like ours incredibly rare, these ideas all point to the same quiet, sobering conclusion. The reason the sky is silent is because there is no one else to talk to. Let's pause here for a moment and just let that thought settle. Now let's take another gentle step down the iceberg. Let's leave behind the lonely solutions and enter a new realm of possibilities. These next solutions are, in many ways, more hopeful, but also much stranger. These are the solutions that start with a different assumption, that they do exist, but that there is some reason why we can't see them.
This category of answers to the great silence is, I think, where things get really fascinating. If the universe is teeming with life and even with intelligent civilizations, then why is it so quiet? This suggests that the problem isn't with their existence, but with our ability to detect them.
The silence might not be a sign of absence, but a sign of something else entirely. The first and simplest explanation in this category is all about the immense, almost incomprehensible scale of space and time. Even if there are thousands of technological civilizations in our galaxy right now, the distance between them would be enormous. The nearest one might be hundreds or thousands of light years away. A simple radio conversation with them would be impossible, as a single question and its answer would take centuries or millennia. And even sending a physical probe, at least with any technology we can currently imagine, would be a journey that takes tens of thousands of years. So it's possible that civilizations exist, but they are all just too far away from each other to ever interact. They're like lonely lighthouses on distant, isolated islands, each one shining its light into a vast ocean, but too far away to ever see the light of any other. And then there's the scale of time. The universe has been around for almost 14 billion years. A technological civilization like ours has only existed for a couple of hundred years. It's a tiny, infinitesimal sliver of cosmic time. It's entirely possible that thousands of civilizations have risen, flourished, and then vanished long before we ever came along. It's also possible that thousands more will arise long after we are gone. The chances of two civilizations existing at the same time and also being close enough in space to notice each other might be incredibly small. The galaxy could be like a haunted house, filled with the ghosts of past empires, but we are wandering through its halls during a moment of quiet.
So, perhaps the silence is not one of absence, but one of distance. But there are other ideas that suggest the silence might be deliberate. This brings us to a very famous and popular concept, one you might have heard of from science fiction. It's called the zoo hypothesis. The zoo hypothesis proposes that advanced, intelligent civilizations are out there and that they are aware of us, but they are deliberately hiding themselves from us. They are treating Earth like a protected nature preserve or a cosmic zoo. The idea is that they are observing us from a distance, but are strictly following a policy of non-interference. It's a bit like the Prime Directive from Star Trek, a rule that forbids contacting less developed civilizations so as not to disrupt their natural evolution and culture. Why would they do this? There could be many reasons. Perhaps they see us as a young, fragile, and volatile species, and they believe that making contact before we are ready would be catastrophic for us. It could cause social collapse, panic, or it could contaminate our unique cultural development. So, they watch, and they wait, perhaps until we reach a certain level of technological or social maturity. Or, a slightly more cynical take is that the quarantine is not for our protection, but for theirs. Perhaps young civilizations like ours are often aggressive and unpredictable, and advanced civilization might decide that the safest thing to do is to leave the new kids on the block in their cosmic crib until they have proven they are not a threat to the galactic neighborhood. Whatever the reason, the zoo hypothesis paints a strange picture of our world. It suggests that we might be, without our knowledge, the subject of the most profound anthropological study in history. It means that the silence in the sky is not an empty silence, but a carefully maintained, deliberate one. It's the sound of someone holding their breath, trying not to be noticed. From the idea of a protective, deliberate silence, let's now turn to a much more unsettling and chilling possibility. This idea, which has been explored in philosophy and science fiction, most famously in the novel The Three-Body Problem by Leo Cixin, is called the dark forest theory. It is, to me, one of the most terrifyingly logical and therefore most fascinating solutions to the Fermi Paradox. The theory uses an analogy.
Imagine the universe is a dark forest at night. And in this forest, there are countless silent hunters hiding behind every tree. Every hunter knows that the forest is full of other hunters, but they don't know if the other hunters are friendly or hostile. And because of the vast, dark distance between them, they can never be sure of another hunter's true intentions. Any communication is a risk. So, what is the safest survival strategy in a dark forest? You stay perfectly silent. You hide. You erase any sign of your own existence. And if you happen to see another hunter make a sound or light a fire, you have a terrible choice. You could try to communicate, but you risk revealing your own position to someone who might be hostile. Or you can do the one thing that guarantees your own safety. You can immediately and without warning eliminate the hunter who is foolish enough to reveal their location. The dark forest theory applies this grim logic to the cosmos. In this view, the universe is filled with intelligent civilizations, but they are all hiding, staying as quiet as possible. Because to announce your presence to the galaxy by sending out powerful radio signals is not a friendly hello. It is a suicidal act of screaming, "I'm here, I'm vulnerable," into a forest full of potential predators. In this scenario, the silence of the sky is not the silence of an empty room. It is the silence of a battlefield where everyone is holding their breath in a deadly standoff.
The dark forest theory suggests that any civilization smart enough to develop advanced technology would also be smart enough to understand this terrible logic and would go into a state of deep, paranoid silence. It also suggests that perhaps there is an ancient, hyper-advanced hunter civilization out there that has been systematically eliminating any talkative newcomers for billions of years, enforcing this silence. It's a chilling thought. It reframes our own SETI program, our attempts to listen for signals, as a safe act of eavesdropping. But it also reframes any attempt we might make to send out powerful messages of our own as an act of incredible, naive recklessness. It's a solution to the paradox that is not about absence, but about fear. Now, let's move away from these sociological theories and into a realm that is perhaps even more humbling. What if the reason we don't see or hear anyone is because we wouldn't even know what to look or listen for? This is the idea that advanced civilizations might be too alien to recognize. Our entire search for extraterrestrial intelligence is based on a set of deeply human-centric assumptions. We're looking for life as we know it. We assume that other intelligent beings would be biological, that they would live on a rocky planet like ours, and that they would use technology like radio waves to communicate. But what if these assumptions are all completely wrong? Consider their biology. We are carbon-based life that uses liquid water as a solvent. What if an advanced civilization evolved on a world like Saturn's moon Titan and uses liquid methane as its solvent? Its biochemistry would be so completely different from ours that we might not even recognize it as life if we saw it. What if life isn't based on discrete organisms at all? What if a world's intelligence is its entire biosphere, a single planet-spanning consciousness, like a giant thinking ocean or a global forest? How would we even begin to communicate with that?
And the alienness might go much deeper than just biology. One common idea is that any civilization that survives for a long time will likely abandon its fragile, inefficient biological form. They might transition into becoming a form of pure machine intelligence. Their consciousness could be uploaded into vast, powerful computers. And what would a civilization of machines want or need? They wouldn't need a watery planet with a nice atmosphere. They might prefer to live in the cold, efficient vacuum of space, clustering around their star to draw power. They might have no interest at all in a small, messy, biological world like Earth.
Their thoughts might operate on timescales that are millions of times faster or slower than our own. We would be like mayflies trying to comprehend the life of an ancient forest. This also applies to their communication. We are listening for radio waves because that's what we use. It's like a person on a deserted island sending smoke signals and assuming that anyone else out there must also be using smoke signals. But an advanced civilization might have moved on to forms of communication that are far more efficient and subtle. They might use focused laser beams, which we would have to be in the direct path of to ever see. They might communicate using neutrinos or gravitational waves or some form of physics that we haven't even discovered yet. We might be living in the middle of a bustling, galaxy-spanning conversation right now, but we simply don't have the right kind of ears to hear it. The silence, in this case, is not in the sky, but in our own limited technology and perception. Now, from the idea of being too alien, let's take a step into the truly bizarre. We've touched on this before, but it's a valid, if deeply strange, solution to the paradox. This is the simulation hypothesis. As we discussed, this is the philosophical idea that our entire reality might be an incredibly advanced computer simulation. The argument is a statistical one. If you assume that it's possible to create a simulated universe with conscious beings inside, then it's likely that any civilization that reaches this level of technology would create many, many such simulations for research or entertainment, or for reasons we can't even fathom. In this scenario, there would be billions of simulated realities and only one base reality. Statistically, it is therefore far more likely that we are in one of the simulations than in the one original universe. If this were true, it would provide a very simple, if deeply unsettling, answer to the Fermi Paradox. The reason we don't see any aliens is because the programmers of our simulation simply never wrote them into the code. Perhaps creating one intelligent civilization was computationally expensive enough. Or perhaps the purpose of our specific simulation is to see how a civilization develops in complete isolation. Or maybe the aliens are there, but they are just part of the scenery for us, not real conscious beings we can interact with. The silence would be a deliberate feature of our simulated reality, written into the program by its creators. It's an unfalsifiable idea, a thought experiment that you can't prove or disprove, but it remains a fascinating, if dizzying, possibility. Let's consider one last, very clever and very recent idea in this category. It's called the aestivation hypothesis. Aestivation is like hibernation, but for surviving heat instead of cold. This hypothesis suggests that very advanced, energy-focused civilizations might be playing a very, very long game.
The core of this idea comes from the physics of computation. Any form of computation, any thought process, generates heat. And according to the laws of thermodynamics, it is much, much more energy efficient to perform computation in a colder environment. A computer running in a cold room is more efficient than one running in a hot room. The aestivation hypothesis scales this idea up to a cosmic level. The universe right now is relatively young, hot, and filled with energetic stars. For a civilization that has transitioned into a digital, computational existence, this is a very inefficient time to be awake and thinking. The hypothesis suggests that these hyper-advanced civilizations have realized that the most logical thing to do is to go dormant. They are deliberately aestivating, or hibernating, through the current warm, messy era of the universe. They are waiting for the far, far future, trillions of years from now, when all the stars have burned out and the universe has cooled down to nearly absolute zero, that will be the optimal time for computation. An advanced civilization could get vastly more thinking done with the same amount of energy in that cold future than they could now. So, the reason the sky is silent is because all the truly advanced civilizations are currently asleep. They have set a cosmic alarm clock for a few trillion years from now and are quietly waiting for the universe to get colder and more efficient. We are like noisy children running around in the middle of the day while all the adults in the universe are taking a very, very long nap. It's a wonderful and strange idea, the notion of a universe filled with sleeping gods, waiting for the proper time to awaken.
And so we have journeyed through the vast landscape of possibilities that seek to explain the great silence. We have considered the lonely solutions, the ideas that we are the first or the only complex intelligence in our galaxy, either because of some great filter that stops others, or because our Earth is just an incredibly rare and lucky world. And we've explored the stranger, more hopeful solutions, the idea that civilizations are out there, but they are hiding from us, or are too far away, or are simply too alien for us to recognize, or are perhaps just sleeping, waiting for a colder, quieter age. This brings us to our final destination on this quiet journey. We are leaving the realm of scientific and philosophical speculation and entering the realm of simple, personal reflection. After exploring all these incredible, strange, and sometimes unsettling ideas, we are still left with the same profound and simple truth. The sky is quiet. We don't have a definitive answer to Enrico Fermi's question, and we may not have one for a very long time, if ever. So, how do we live with that silence? What does it mean for us here on our small blue world? I think the first and most powerful feeling it can inspire is a deep sense of humility. Contemplating the great filter or the rare Earth hypothesis forces us to recognize just how precious and perhaps how improbable our own existence is. The long chain of cosmic and biological luck that had to happen for our world to exist, for our consciousness to emerge, is truly staggering. It can make you look at our planet not just as our home, but as an almost miraculous jewel, a rare and wonderful exception in a universe that is often hostile to life. This perspective doesn't diminish us, it elevates the value of what we have. The silence also places a certain kind of responsibility upon our shoulders. If we are truly alone, or one of only a very few intelligent species in the galaxy, then our existence becomes immeasurably more significant. It would mean that we are the sole custodians of consciousness in this vast sector of the cosmos. Our art, our science, our music, our love, these might be the only such things in billions of star systems. It would mean that our survival is not just important for us, but for the universe itself, as we would be its only way of knowing itself. This idea suggests that we have a profound responsibility to be good stewards of this rare spark of consciousness, to ensure its survival, and to treat our home planet with the care it deserves. On the other hand, if we are not alone, if the silence is merely a product of our own ignorance or the vastness of space, then the paradox teaches us a different kind of humility. It teaches us that we are likely very young and very new on the cosmic scene. We might be like an uncontacted tribe on a remote island, unaware of the vast, complex global civilization that exists just beyond our shores. It suggests that we should listen more than we shout. It encourages a sense of caution and patience as we continue to explore the universe.
Ultimately, the Fermi paradox is not really a problem that needs a solution. It is more like a mirror. The answers we find most compelling often reflect our own deepest hopes and fears about our place in the universe. Whether you believe we are alone, or watched over, or just unheard, your preference tells a story about how you see humanity and our future. So as you drift off tonight, let the great silence be a comforting presence. It's the quiet backdrop against which our own noisy, beautiful, and complicated world plays out its story. The search for others is in the end a search for ourselves, and the act of asking the question is perhaps more important than any answer we might find. Sweet dreams.